All right, hello everybody. My name is Scott Gray. I am a senior architect and senior technical staff member at IBM. This is the first of two what I'll call nerd talks. I'm not really going to talk about a product in particular. I'm going to talk about a few technologies, but not really focused on any specific one. Sorry, I'm about to feedback. Let me lower it a little bit. Hopefully that'll be better. So, but mainly what I wanted to talk about, so I've been working for the last 3 years on IBM's Big SQL. That's my only plug. You should check it out. It's a great database product. But in particular, for the last revision, I've been focused very heavily on making Big SQL work against NoSQL, specifically against HBase. I've been working with HBase in the past, but it's kind of some interesting things happen when the two worlds come together. When you try to introduce SQL, which is very structured, very rigid in its schema, to a system which has no rules, literally has no rules. And so what I wanted to do was really just share what I learned, when we're building the product. And maybe you can take some of that away and apply it to your future aspirations for running SQL on NoSQL. And not to say that it can't be done, there's just some things you have to consider, and that's kind of what I wanted to raise some awareness. And then I'll plug my other talk, which is along the same lines, kind of as we proceed through this. As a warning, I probably have a little bit too much material for the time allotted. I might skip over some slides or move quickly. If I do run out of time, just come up after, or we'll meet out in the hall, and I'm happy to talk about stuff. So I'm going to talk a little bit about SQL, the obligatory, a little bit about where it came from, pros and cons of SQL, and specifically kind of to frame the argument for where NoSQL came from, or why it's become so popular. And also to frame, there's some challenges that Hadoop itself imposes on SQL, which NoSQL was sort of built to solve. And so it's to put all that into perspective. And then finally, we'll dive into NoSQL and how it solves these problems, but how you have some trade-offs. If you choose to use some of the features of NoSQL to its fullest extent, you might be giving up a little bit on what you could be doing if you were to just stick with the pure NoSQL world. I won't spend much time. Structured SQL has been around for a very long time. Started in the 70s by IBM, by us. And really its big claim to fame, I think, is it's been around a long time, it's ubiquitous, most importantly, it's standardized and fairly heavily standardized. So skills are portable, tools are portable, software is moderately portable between systems. Its defining characteristics, and you can argue any one of these, but I think hopefully everybody would generally agree that its defining characteristics are the data's tabular, maybe stored columnar, but it's tabular. It defines itself with a strict schema, and yes, I'll address drill for you drill folks in a little bit, but it tends to have a strict schema, and it highly encourages a relational design, and for good reasons. So SQL itself, what's to like? Well, you have the obvious ones. It's well known. Everybody, you're probably here because you know it. Anybody who doesn't know SQL, raise your hand, and then please leave the room. So the standardization makes both skills portable, makes technology portable. It allows for many, many tools. It's got a very rich ecosystem of tools. And most importantly is the relational model behind SQL allows for dynamic ways of slicing and dicing and looking at your data, whether it's sales by part, sales by region. These are all just matters of framing your queries and doing your joins a little bit differently. But there's kind of some not so obvious aspects of SQL. So this comes from having worked on a relational database engine for some time now. So the not so obvious parts, I talked about the slicing and dicing. Well, the obvious upside of SQL is when you create your query, you create it with what do I want? You don't care how do I get it. And it's the optimizer's job, the query optimizer, to figure out how do I get it. And it's taking advantage of this relational model. It's taking advantage of this strict schema. And there's a lot that it can learn by looking at the schema. Well, we've got the obvious. I guess this doesn't come from schema, but you have things like statistics. Well, statistics are kind of tied to the schema because you tend to tie this column, which is this type, has this distribution of data. That leads to most of the modern optimization technologies. It can take advantage of things like what's the size of the data? What's the size of my row? What are the size of my columns? How many rows can I fit in a page? how big a buffer pool do I need to handle this query? And all this can be gleaned by, and all that leads to I/O costs. How much does it cost to read this thing off a disk? How much is it going to cost to take my rows, my projection, and ship it across the network? That's all costing. That's all optimization stuff, and that's all learned by having metadata. Including data type domains. If I'm joining a tiny int to a small int, I know I can skip any rows that aren't between -127 and 128, or vice versa. If I've got a check constraint, the same thing. If I'm joining to a column that has a check constraint, I know in the joining table I can ignore any row. I could kind of throw a free where clause, and I can ignore any row that wouldn't match that check constraint. And things like referential integrity. If I know I've got a parent-child relationship, I'm joining two tables, and I know because of referential integrity, I can never have more than one row matching a row in my outer table. As soon as I find a row on that inner table, I can stop. I don't need to search anymore. So I've got metadata, I've got information. I can be smart about my access patterns. The optimizer can do its job. So there's a trade-off, of course, and this is kind of where part of where NoSQL grew from. I kind of skipped the first one. This is just kind of storage. It's not really, it typically hasn't been ideal for sparse data, but there's some technologies out there that are helping there. But I think most importantly that this very rigid, very simple, highly normalized model of data makes things hard to work with in some cases. You take a persistence layer, which might be, say, taking an object in your programming language and persisting it to the relational database. That one object now may blow out into 12, 20 tables. When I want to read that one object back, I've got to do a great big join and gather all that back up. And for what? Maybe that's my only access pattern, store and retrieve this object. And it's very irritating now. If anybody, if you work with Hive, the Hive metastore is exactly a case of this, where I have a table, and I tend to want to look up a table. But behind the scenes, it's got to join like 90 things together to pull it back. And in fact, you'll see that Hive has got a project underway to move its metastore into HBase and store everything about a table in one row. Says, great, I'm going to go fetch a table. Bam, I got it back. And then finally, I think these last two major bullets are tied together, that the relational model, through all the glorious benefits of a nice rigid schema, it's rigid. To make changes to it is an expensive proposition. Any of you with a major enterprise data warehouse, if you need to go change a data type in a column, the cascading effect of what happens when I change that type, I might need to rebuild that table to change the type. And now what about all the tables that referred to it? And what about all the tables that referred to those? And it can be a huge pain just to do a simple change. So it makes it difficult to be agile. And if this is the most agile period I have ever experienced in technology. Things are running at 1,000 miles an hour, and people don't have time to wait for these sorts of changes. And again, I think this is where the strengths of NoSQL come into play. I'm going to take a little sidetrack from talking about the pros and cons of SQL to mention one thing. So I'm hounding on this rigid schema thing, and those of you that have looked at Apache Drill is a really cool project, and its claim to fame is it can run SQL against data with no schema, without knowing the schema in advance. It needs to know the encoding, it needs to know, yes, this is JSON data, but it doesn't care what the schema is. It learns that on the fly, and it begins applying where predicates to the data on the fly as it goes. You should check it out, it's really cool. So it solves that problem, but it doesn't solve the other relational problems. So the language problem of applying SQL to no schema, they've solved. But you still have the fact that you may be modeling things relationally. It's still got to do joins, and I'll talk about joins in a second and why that's important. It's difficult to make optimization decisions if you don't know what every row is going to look like in advance. They have some ways to do some crude optimization, and they'll get smarter and smarter about it, I'm sure. But I don't know if they'll ever catch up to what you can do when you know absolutely everything about your data. And finally, this is just kind of a minor nitpick, but I talked about tooling. The other thing about tooling is being able to browse your data, to walk through the data model and visually construct queries. And when you don't know the schema, how do you do that? So they can solve the problem of querying, but not really the problem of how do I explore visually, how do I put together and pre-decide what I want to query. So anyway, but I still encourage you to look at it. It's a neat project. So the last part, I know I'm supposed to be talking about NoSQL, and I'm about to get to it. But the last thing I wanted to talk about was SQL on Hadoop, and specifically. So I went through pros and cons of the language itself, but SQL on Hadoop itself directly poses some challenge to the relational model. I encourage you to come visit my second nerd talk tomorrow at 3:10, where I'm going to talk about this in some depth. Not as much depth. There's not enough time for me to go in the depth that I wanted to, but I'm going to talk deeper about this specific topic. But so I picked this is a slide from that deck, but it's to talk about one of the problems, which is data placement. So in a traditional data warehouse, a node owns data. I say, I'm going to partition this table, I'm going to partition it this way, and maybe this node over here owns all of the data for users beginning from the letter A to the letter C. And this guy owns letter D to E. And then I might take another table and partition it exactly the same way. So now I know that if I'm going to join those two tables together, I can, in parallel, I can have every node join their local data together, do all the filtering, all the joining, and then maybe take the final artifact from that and ship it off to another node to finish my query processing. And that's pretty much without fail, that's the major parallel processing trick of most enterprise data warehouses. So Hadoop does away with the ability to do that. I won't say does away. There are some tricks. They're just beginning to get explored, and I will, if there's time, I'll talk about it in the other presentation. But basically, HDFS is built around random data placement. I throw a block out there, and it's out there somewhere. So now you think about two tables. When I'm writing the data for my two tables, I write them, and each block is somewhere out in this big cloud of machines. So when I go to join them, how do I do it? I don't have this idea of co-location anymore. I can't do a local join, more or less. Again, there's tricks, but they're not easy to do on purely big data. This is just to give you kind of a flavor of what really happens. When we're looking at almost any of the query engines, Hive, Impala, BigSQL, Drill, any of them, they all have to kind of resort to a couple basic approaches. And one is what's called a redistribution join, which is, so as I've got a set of nodes on your left. I've got two nodes reading data from table T1. I've got one node reading data from table T2, which I'm joining. Each one's reading the rows, and maybe they're applying whatever where predicates they can. They're filtering rows. But to join them, the data is on entirely different machines, so what they have to do is they have to pick another machine in the cluster and say, let's say it's an employee department join. I might say, I'm going to pick a node to join all the data from department 1. So each of these machines at the top that are reading their data are shipping all the department 1 data to one node, and then all the department 2 data to another node, and that's what the color-coded lines indicate. I'm shipping all my data. Now imagine a join with no other where clauses, with no other filters on it. I might move those two tables in their entirety, those two 1.5 petabyte tables, I might move them across the network to do this join. That's worst case. It tends not to be that way, but that's worst case. And anyway, there's another approach called a hash join, but I won't spend any more time on it, given my time here. But again, it involves taking at least one table, filtering it, and shipping it to every node in the cluster. So, and that's the price you pay. That's the price you pay for this Hadoop data model. Again, there's tricks, but somebody invariably will run across this. So now, okay, so I've set up all the pros and cons, and by the way, I don't want to scare you off. I develop a SQL on Hadoop solution. Most of these problems are solvable, and they work in the vast majority of cases, but you just have to understand in your head, this is how it works. But okay, so now, NoSQL. So NoSQL, I won't say it came about to solve these challenges, because the reality is NoSQL has been around longer than SQL. The first database was created by TRW in 1965. Yes, that's even older than me. We've got, in 66, IBM introduced IMS, and then later on Hadoop, I believe the progenitor of the NoSQL on Hadoop came from Google's Google's big table papers. And the defining characteristics are They have no predefined schema, by and large. Again, there's a lot of them out there, but usually they have no they might have an encoding. They might say we store a JSON document, but there's no schema, generally. They're designed for horizontal scale out, meaning that as a node maybe becomes full, it's easy to just throw another node on the cluster and it becomes part of the whole game plan. They encourage a data model where related data tends to be either nested within a row, and I'll give some examples of this, are either nested or they're physically co-located. But basically what it is they really encourage the opposite. They encourage a non-relational design. And because of all the flexibility they provide, they tend to not have exactly like a full rich SQL or full rich query language. Like SQL, they might have more API or kind of path expression oriented languages. And again, I might be overgeneralizing in some cases, but that tends to be the defining factors. And what I'm going to do now, I'm going to talk mainly just because the one I have the real world experience on is HBase. So I'm going to talk about this specifically in the case of HBase. And probably most of you here are familiar with HBase. So I have my little HBase summary in a slide. So HBase is a client-server database on Hadoop. A table has no schema. That was one of my defining factors. If you go ask HBase what table T1 looks like, it says it looks like T1. It knows almost nothing else about it. There's a table called T1, yes. They are all HBase tables they have a row key, and they are ordered and accessed by row key, so you can look up a single row very, very quickly. And by the way, a given node owns a range of rows. When that node fills up, the node will break into two, split itself into two, and each one will take approximately half of the data that was there. So it automatically scales up and it automatically scales out as it goes. And then within that, so every row can have one or more groups of name value pairs. I treat them like hash tables if you're a developer. But they have one or more name value pairs. They call them column families, and I guess you could call them columns, but you can have one or more groups of columns. But it doesn't say anything about the columns or the name value pairs that are in a row. Every row can be completely different. Every row can have a totally different set of name value pairs. One row could have none. The next row might have 1,000. It's entirely up to you on what those name value pairs mean. So, in a traditional, well, actually, I'll look at it from this perspective. So, if you're using a NoSQL database in a form kind of most befitting of SQL access, you would do something like, you would model your table almost like a regular relational table. So what I've got here is I've got some syntax. Again, I said I wasn't going to plug big SQL, but I am going to use it as an example. So this is our syntax for defining a relational table against an HBase table. Now, all we're doing is we have at the top, we have the usual syntax for defining what columns, their data types, and so on. That's a relational view of it. And then at the bottom, we describe how to map it. So we say the row key is comprised of the values in C1 and C2. Those two make up my row, quote unquote, my primary key, my row key. I might have my next two columns, C3 and C4, are going to be stored in a column called column 1 and a column family called CF. Anyway, the details aren't that important, but what I'm doing is I'm mapping, that here's here's the name value pair over here in HBase, and here's how I want it to appear relationally. So this is a fairly simple data model. It's not quite one-to-one. I might store two values in one HBase column that'll become two columns in my relational view, but more or less it's a straight mapping. But what this design does is it kind of compromises the power that you can get from using HBase or using a NoSQL database to its fullest potential. So let me give you an example of this. So one of the common HBase design patterns, and I would say of most NoSQL database design patterns, would be to denormalize. To say, in this example is a department-employee relationship. I've got a department table relationally, and each department has employees. Well, what I'm doing in this, and I'll try to explain it the best I can with my little drawings down here, is what I've done is I've stored in a single row contains everything about the department and everything about all the employees in the department. That what I've done is, so row 001 is my department for finance. And I have a column family called department info with name value pairs, and I've got information about its finance. It's managed by Bob Smith. Here's his phone number, here's his address, and so on. And then I have another one where my name value pairs are a little stranger, that instead of having a traditional, like a column name, implicitly my key and my name value, or my key value pairs are, the key is the employee ID, and the value is a JSON record. Now remember I said HBase has no data types, so you could store them however you wanted in there. In this case, I happen to choose a string and with JSON in it. So now I can have as many employees as I want in here, and HBase allows you to add and remove individual names and values from a row. So I can continuously update and change my employees, but if I want to know everything about a department, I can do it in one read. Give me row 1, and I've got everything about that department in one fetch. And which has, actually I'll talk about some of the advantages of that model in a second. Or here's another example, which I think is a little more clever, but a little less often seen. One is to use row adjacency, meaning I mentioned that all tables are ordered by row key. So in this case, what I do is I've got my row key for some rows is just the department ID. And then in other cases, it's the department ID plus the employee ID. And what that causes is because everything is ordered in HBase and stored ordered, they're adjacent, physically adjacent. And so what that means is, so if I want to fetch just the department, I ask for 001. If I want to fetch all the employees, I can say, give me everything from between 001 and 002 exclusive. And that will fetch all the departments and employees together. And it's very efficient because it's called a range scan in HBase, which is a very efficient operation. And the odds are good that any given server will physically have all the employees and all the departments there together at any given time. So you can hopefully, I know I'm going through these drawings fairly quickly, but hopefully you can see the sky's the limit with weirdness you can play with this data model when it doesn't care how many columns, what a row looks like. And there's other similar design approaches. But there's trade-offs. The biggest thing with this whole kind of nested data model is that data is always co-located. There's no join anymore. It's zero cost to look up all the employees. And also as data shards, I mentioned when a server fills up, when it gets so many rows, it splits into two. One takes half of the rows, the other takes the other half of the rows. Well, the nice thing is all that data, I mentioned the co-location problem with Hadoop. Well, I don't need to worry about it anymore. The data is physically bound together, so there's no more problem of co-location. And schema is trivial to extend in the future. Going briefly back to my pictures here, I could take this one with adjacent rows. Well, maybe an employee can have multiple phone numbers. I could do something like, say, employee or department/employee/phone number, and then I could have information about it's his mobile number, only call it during the week, and I could do that just without thinking about it. I just throw in another row in HBase, and all of a sudden I've got new data. No, didn't have to worry about the schema. I didn't have to declare anything. I stuffed new data out there. Instantaneous data model change, and that's the great part. So it's trivial to expand it. So I can add more name value pairs, I can add more adjacent rows, but the problem is the relationships tend to be one way. I pre-decided that my department is the top level thing, and that so the relationship is always go from department to employee. But what if I needed to ask the opposite question? What department is Bob in? Well, finding Bob now, I have to search through every single department and every single employee. And I will say there's indexing. Big SQL has an indexing technology for HBase, and there are some indexes out there. But by and large, unless you think in advance to do this, you're kind of stuck with that data model you decided up front. And certain relationships, or certain questions are really hard to answer. But more importantly, now what if I join my employees, forget about department, I join my employees to something else, some other table out there. Again, now I have to sift through every department to go find the employees to go do that join. Now the other problem is just one of modeling. So I showed you that example a few slides back of my create table statement. How do I define a table against my data model? And my example was a simple one, one-to-one almost. I've got this relational column, it's over here in this HBase column. But now think about these ones I just showed you. Imagine the create table statement, which would allow me to try to describe this relationship, this nesting of data. And I've spent a lot of time trying to imagine it because we've got customers that have this data model and they want to run they want to use SQL on it. And we don't really have a good solution. I mean, I can invent one for that one customer case, but it probably won't work for the next because there was no data model, there's no rules to this game in the HBase world. There are some cases. Hive actually has a kind of elegant solution for kind of this example, where what you can do is you can say, fetch everything in the employees column family into a hash table, into a map. And so I can then probe into that. And so they have a way kind of to handle it, but it doesn't work very deeply. From there, if I wanted to say, for employees between 287 and 934 whose first names are Scott, it becomes a really weird, awkward mess in Hive so I'm not poking at Hive. I don't think many people other than Drill's beginning to hone in on this. But it's a difficult problem to solve. And I think when you're modeling your table, depending on the decisions you make on how you want to lay it out in HBase, you may have the most optimal HBase application ever. Very, very, very efficient. But you may have screwed yourself when along comes a manager and says, we want to run Tableau against this. We want to run, SQL queries against this. You may have a really, really, really difficult time trying to figure out how to model this thing in the SQL world. And then in terms of query optimization, there is none. You made that decision. When you modeled this thing, you made your decision on how the data is going to be accessed by the mere way you modeled the data. There's not many options to be played anymore. And again, this is actually a place where things are changing. I've seen some grumblings in the MongoDB world where they're having a join model where you can express joins and they'll have some statistics of some sort to try to help figure that out. But it's kind of in its infancy and it'll be tough to match what you can get with SQL. And then the last part still hasn't changed from a tooling standpoint. If I want to just point a tool at HBase and browse around, it's not really possible. It's not very easy anyway. Okay, now we're back to the original problem. Why not then just go back to this one-to-one relational model of a table in SQL to a table in HBase? My department table and my employee table. Well, there's a couple reasons for this, or there's a couple reasons why this isn't probably a brilliant idea. You can do it, and it's optimal for ease of use in SQL. But you're back to one of the original problems that now, one of the things I didn't talk about is where does data live in HBase? I said a given server would host a range of data, but it's more or less random which server is going to own that region. And in my other talk, I'm going to touch on co-location in HBase. There's some tricks that people are starting to play, but generally, so now in my little diagram here, I've got a region which might have departments 001 to 468 and one that has employees 1 to 300. But when I'm joining those together, some random set of employees will belong to some random set of departments somewhere out on the cluster. So again, you're back to this having to move data between nodes to do the join. And once again, you're back to those original problems. I had a big complex object and I'm now trying to model it, and it blew out to 12 or 15 tables, and I have to rejoin those 12 or 15 tables to get back to my original model. So again, this works, and actually it's not even necessarily a bad idea because you still get all the other benefits. I think I didn't touch on it, but HBase is one of the few Hadoop technologies that can do very efficient updates and deletes, can very efficiently fetch a row, And so for many use cases, this may be just fine. But if you're looking to do very, very large-scale joins, it doesn't solve the problem. So is all lost? No, it's not all lost. I wish I could say that this was going to be a tutorial on how to do it right. There is no tutorial on how to do this right. Mainly, it's here to let you think, or to make you think about the problem. So one option is you can sort of mix and match. You can expose portions of your table through SQL, meaning that in some of those data models I gave before with adjacent rows, or with using column families to store nested data, maybe some of that information, maybe the nested data you ignore, and maybe you just build a SQL view of the department data. We've got other customers that have been doing things like, HBase has these things called coprocessors. They're kind of like triggers in SQL. So whenever you do an operation, they can intercept the operation and do something else. So in some cases, we've had customers that will do things like maintain a normalized SQL view of the table, of the data, off into another table. And that will always stay in sync thanks to the fact that the coprocessor is always intercepting the data. If you delete the original row, it can go delete the kind of SQL relational view of the row. And the other thing is get to know your SQL solution. Get to know it well. So some of them have, try to tackle some of these data models. I mentioned Hive. So Hive does have the ability to take some arbitrary data from HBase and expose it via a data structure called a map in Hive. And with BigSQL, we have the ability to allow you to write your own custom plugin that can read, say, a nested piece of data, can read some complex piece of data in whatever random encoding you've chosen, and can map it to one of the data types that BigSQL supports, like an array or a struct or something that sort of represents that nesting. And then, again, earlier I mentioned drill. Drill has a huge potential in this space where not all of I don't think it could easily tackle all of those data models, although I'm happy for somebody to show me how. Maybe it can. But it does kind of have this ability to walk down in an elegant fashion through this complex nested data and find answers. So basically, I think you can get away with kind of mix and matching, but it's something where you need to consider well up front. You need to start thinking about before you build your data model. Am I going to run SQL against this? Do I need to run it? How efficient do I need it? And what are all the trade-offs? And there's a lot of trade-offs. And I'll reiterate my disclaimer here. So I've been focusing on HBase. I probably don't overgeneralize everything I've said about HBase to other solutions. There are a lot of other solutions. Some do tackle some of these problems, but I would say by and large, at least one of the problems I've described here would be true for any given NoSQL solution. Actually, one of the more, since I have just another minute, I'll mention one of the other interesting problems we were looking at using at pointing Big SQL at a NoSQL solution that's eventually consistent. And what eventually consistent means is that unlike HBase, where one server owns one row, so always go to that server. An eventually consistent database is multiple servers may or may not have a copy of the row, and when I read a row, I have to go out to other servers to validate, was this the right version? Was this the right view of the data? Somebody may have updated it, and this might be old. So you actually, and one of the interesting things that poses is if you're scanning a large set of data, like say for a join, I can't just go to one server and start reading all the data it has. I have to read all of its data and then go ask another server to verify, to validate that the row I just read is still a valid row. So it leads to other problems with SQL, accessing SQL against a NoSQL database. So anyway, the long story short, this is a long-winded way of saying think about it. Think about, and I'm not saying don't use NoSQL. It's excellent, but think about what you want to use it for. Think about if you need to use SQL. Maybe you don't, and then it's fine. SQL's not the solution to everything. But think about it. And make sure you understand in advance your chosen SQL solution, what can it do? What is it capable of modeling from a NoSQL database? And anyway, if there was more time, there's more interesting things to talk about. And as I said, to replug my next session tomorrow, I'm going to be focusing just purely on SQL on Hadoop and more of the challenges there. And even then, I could fill 3 or 4 hours with that. But hopefully this was useful, and that's all I had to talk about. So I'll open up the floor to questions, and also to poke holes if I said something wrong, which is fine too. Yeah.
Other than the schema on read issue, I mean, why didn't you just map like a shared country database like DB2 or Heritage and HBase that way? Is this the schema on read issue?
Well, so the question was about schema on read. So why didn't we just take a relational database and map it to data on Hadoop? Yeah, actually, that's what big SQL is. The main advantage of the NoSQL, however, as I said, it's one of the few, specifically HBase, it's one of the few that support update and delete on HDFS. So if we pointed it to your traditional flat file HDFS data, your hands are fairly tied if you need to look up one row quickly. So I mean, there's advantages to the NoSQL store. But anyway, that's what Big SQL is. But it looks at both the data on HDFS as well as data in HBase. Any other questions? Yeah. So the question was, what do I think about NoSQL design? Do you mean modeling your tables? What do I think about modeling your tables purely relationally? Just because you still have the ability to do cheap row reads and cheap updates and deletes? Yeah. So, yeah.
You duplicate data, yes, right. You duplicate data, but since the writing data is cheap, relatively cheap operation to anything else, so you can have.
Okay. So yeah, I'll try to restate that real quickly. So since it's also being recorded, but yeah. So it was I mentioned so you've got your data denormalized in one particular fashion for one particular access pattern. Department to employee. Well, writes are cheap in a NoSQL database, so why not just say, okay, fine, and I'm going to replicate my data joined another way. Maybe invert that join or pull other data together. And yeah, that's absolutely true. I would argue, though, it's not quite as cheap as you would think. I can tell you that we have an indexing solution on Big SQL, and which is effectively the same thing. Every time I write a piece of data over here, invert it, write another row to another table, which acts as the index. And and yes, it's cheap, but it's now twice as expensive. 2 writes are, no matter what, 2 writes are more expensive, or twice as expensive as 1, and probably a little bit more than twice. So yeah, it's all depends on how much, what sort of data rates you need. But yeah, that's absolutely possible, and certainly people do it. I think I have 1 minute left if there's any other questions. If not, well, thank you very much. I hope this was useful.